All right, guys, so we're going to talk about acids, bases, and the pH scale today. And this is something that is obviously something that's going to follow you all the way into high school. Science 10 for sure, anything in chemistry. This is really part of the nature of the chemical unit. And we've been talking about chemicals in our environment, but we're going to have to bring it back to what the pH and what bases are in our environment. So we're going to be talking about something called the pH scale. Maybe you've seen it in grade 5. Maybe you just sort of talked about it. So here we go. The first thing that we want to talk about is that we want to think about things that are familiar to us for our acids and bases. And so what we have here are some limes, some Coca-Cola. Certain things are acids, certain things are bases. So obviously I have some lemon juice, and we know that this lemon juice is an acid. We know that it tastes sour, so we know it's an acid. I also have something on the table that's baking soda. Baking soda is basic, and so we just have a few things. I've got some chemicals here, hydrochloric acid and sulfuric acid, obviously extreme acids in the acid scale. And then something that's an extreme base on the base scale is actually Drano. Drano is a huge base, and so we're going to test that in a bit. And so those are some of the differences there that you've seen before. So what are some properties of acids? So we need to take a look. And what we need to know is that they always taste sour. Okay, so if you eat them, you know it's an acid if it has a sour taste. It turns litmus paper red. So there's two different kinds of litmus paper. There's this red litmus paper and there's blue litmus paper. Red litmus paper turns red in acids and blue in bases, and blue litmus paper turns red in acids and blue in bases. So B is for base. Just remember that. Red is acid, B is for base. I'll show you these in a second, but you just have to remember that if it's a base, it's going to turn blue because it starts with the letter B. Okay? Cool, so we know that. Acids also conduct electricity. They're really good electrolytes. And so if you were to literally put two lines or electrical lines inside of a vat of acid, the electrical current would travel through the acid very, very quickly. It also is corrosive to metals. We learn about this in the very beginning of the year. We know that acids are going to eat through metals, eat through my sink, eat through my hand. That's what acids do. And they obviously react with all metals. Okay, and so acids react with bases to produce salts and waters. This is called neutralization, and we'll get to this in the later slides. But neutralization is an extremely important concept that you need to know now and that you need to know in grade 10. Neutralization is when the pH is 7 and it doesn't hurt anything. It's not acidic and it's not basic. And when you produce and when you neutralize something, it actually gives you water, which this is right here, and it's not going to hurt anyone, and it also produces a little bit of salt, which we know if you put salt in water, it's not really going to be that harmful. All right? So what are some properties of bases? So now we're looking at our bases here, and we want to know what properties are those things, okay? And so bases always have a taste that's bitter. So it's like that chocolate. It's kind of gross, kind of pasty. It always turns litmus paper blue. So if you've got blue paper and you use it, because B is for base, it'll always stay blue. So if I dump the litmus paper into this, it would stay blue. If we use red litmus paper, it's going to turn this litmus paper blue because B is for base. Red is for acid, okay? It conducts electricity, which basically means that as well, if you put a big vat of Drano into a cup and you stuck 2 electrodes in it, it would actually conduct electricity. Very corrosive. So it also is able to corrode things. It's just that bases don't necessarily corrode metals, which is why you can pour Drano down the drain. It actually corrodes and eats through the disgusting hair that you have in the drain, and it burns through it so that you can actually have a nice shower. It feels slippery, so it has a sensation or a feeling to it, and they react with acids. So bases react with acids to produce salts and waters, which is neutralization. So when you put a base with an acid, it neutralizes and it makes water and salt. All right, so what are some examples of acids? So here you're going to see some relatively large examples of acids that you'll see in the future. So acetic acid, that's in vinegar. Absorbic acid is found in citric fruits, so like oranges and limes and stuff. Hydrochloric acid, which I have some right here, is found in your stomach, all right? We've got phosphoric acid is found in fertilizers and in soft drinks. So in your Coca-Cola, there's phosphoric acid that's making it acidic. all right? And the last one is nitric acid, and it's used in some explosive things like dynamite. What's some examples of some bases that you're recognizing? All right, so ammonia, NH3, all right, it's often found in cleaning products. So basically ammonia is found in like your Tide or stuff like that. It's just a cleaning substance. Potassium hydroxide, KOH, has many industry uses and can be a precursor to making soaps. So actually what I have right here is a bottle of shampoo, and we know that that shampoo, and this is actually that Head and Shoulder stuff, it's super basic. You know why? Because it eats your dandruff away. And that's why it actually has some warnings on the bottle, because it's super basic. And so that's something there. Sodium bicarbonate is found in baking soda. So NaHCO3 is found in this baking soda. That's the chemical that's found in here, extremely basic. And we've got calcium carbonate, which is found in antacids like Tums or like anything that you're chewing, like the Rolaids or stuff like that. And then sodium hydroxide is found in lye. And so that's just kind of a cleaning supply as well. So here's just a summary of what we just talked about for the properties of acids and bases. You'll need to know this for the worksheet that you're about to do, but acids taste sour, they don't feel slippery, their pH is lower than 7, which we'll talk about in a sec. They release hydrogen ions, which is extremely important, which we'll talk about in a second. They corrode metals, which we talked about. They react with metals to produce hydrogen gas, and they turn litmus paper red or pink. When we look over to bases, we know they taste bitter and that they feel slippery. Their pH is greater than 7, so 7 to 14. They release hydroxide ions. That's extremely important, especially in grade 10. You need to understand that bases release something called OH. All right, they don't corrode metals, but they do react with other things like hair and gross stuff. And they do not react with metals to make that hydrogen gas, and they turn blue in litmus paper, okay? Awesome. So what's an example of acids and bases you might have around your house? So here's some acids, some more, vitamin C all the way through, lemons, limes, all that stuff like that. Baking soda, you got drain cleaner, window cleaner, any type of soap, any type of shampoo, those are your bases. Cool. So the strength of acids. This is extremely important because now we're starting to characterize into the more scientific piece of acids and bases. So strong acids ionize or disassociate completely in aqueous solutions. What that means is that acids actually break things apart, and they themselves break apart, forming hydrogen H+ ions. That H+ is extremely important because when we think of the word pH, it literally means acids. H stands for hydrogen, and the more hydrogen you have, the more acidic something is. A strong acid is a strong electrolyte, and it really conducts electricity super well. A weak acid will not completely ionize in an aqueous solution, which basically means that there won't be as many hydrogen ions inside of that solution, so that it won't conduct electricity as well, it won't be as strong, it won't burn my finger as much if I dip it in there. So if I dip my finger into this lemon citrus, I'm not going to burn myself because the acid isn't as strong as this sulfuric or hydrochloric acid I have on my table. If I put my hand in it, then you can kiss it goodbye. A weak acid will be a weak electrolyte, again, which means it won't conduct electricity really well. Sulfuric acid, which I have here, is the strongest acid that we have here in the school or in the lab. It is a very strong acid. Phosphoric acid is a weak acid, and that's the stuff. So we'll talk about the strength of bases. So now we're going to talk about how strong bases completely disassociate into something called OH, or hydroxide ions, and they're in aqueous solutions. Aqueous means it dissolves in water, if you didn't remember from last year. So the most important thing you have to know is that bases usually are made up of hydroxide, OH. If you can remember that for next year, you'll be way ahead. So when we talked about acids, we talked about how acids disassociate into hydrogen ions, so pH, H+, hydrogen. Well, bases break down into OH, hydroxide. Okay? Strong bases are also strong electrolytes. They also conduct electricity super well, and not all bases are ionic compounds. So some things like ammonia, they are molecular compounds because N and H are on the same side. Sodium hydroxide is a strong base, and ammonia is a weak base. So just some examples of bases, but remember they break down into OH. So the more O's and H's you have in that acid, the stronger it's going to be. Measuring the strength of acids and bases. So the amount of hydronium or hydrogen ions, H+, okay, we talk about hydrogen being H+, and hydroxide, OH ions in the solution can be detected by various chemicals or by devices called a pH meter. I happen to have one right here. This device reads the pH of anything, and actually often they use these devices to measure the pH in things like hot tubs or swimming pools just to make sure that the pH level is on point. pH is measured with a number between 0 and 14. You have to know that, all right? That's the pH scale, all right? This is a value that reflects the negative of the common logarithm of an ion concentration. Basically what it means is how much hydrogen is in it, and I'll talk to you about it in a second. A pH meter measures the pH volume of a substance. So pH, you guys, the scale ranges from 0 to 14, and it's a way to basically measure how strong or how weak an acid is, or how strong or how weak a base is. pH stands for power of hydrogen. P for power, H for hydrogen. Remember, the more hydrogens there are, the more acidic something is. And so basically, acids are always less than 7. So 0, 1, 2, 3, 4, 5, 6, and up to 6.9 is an acid. The further you get closer to the 0, the more acidic it is. And bases are more than 7. So we're talking like 7.1 all the way to 8, 9, 10, 11, 12, 13, 14. That's a base, all right? Neutral is always 7, and we basically key that in with water. Water is neutral. Water is 7. It has a pH of 7. It doesn't hurt you, harm you. It's not basic. It's not acidic. It's just right in the middle. So the pH scale stands for the French word purvier. I don't even know how to say it. Pouvoir. So I actually took French to grade 12, but that's bad. Hydrogen, anyways, meaning the power of hydrogen, which we talked about. And so there you can take a look at this chart. You see that the most acidic substances are actually at a pH of like 0 or 0.1 or even just 1. And the most, basic bases are all the way at the 14. So that's how the scale works. So you just take a look at increasing acidity going from 7 to 0 and increasing base going from 7 to 14. So just make sure that you understand that the scale gets read backwards on both sides, all right? Acids and bases and the pH scale. So again, I just want to reiterate about these hydrogen ions and these hydroxide ions because you've got to understand it. When we're talking about an acid, we're talking about hydrogen ions. The more hydrogen ions there are, the more acidic it is. If you look at the chart there, you'll notice that at 7, you've got some hydrogen ions and some OH. So that's a mix of both the hydrogen, which is the acidic piece, and the OH, which is the basic piece, so it makes it neutral. 7 is neutral. But as you get more acidic, going towards the 0, going towards the 1, look at all of the hydrogen ions that start to show up. The hydroxide ions start to go away and more hydrogen starts to come. If we look on the other side of things, on the basic side, you notice that as you get more basic, you get more hydroxide ions, which is the OHs. So more OHs means more basic. So as the strength of the acid increases, the strength of the hydrogen ions increases and decreases the OH. And we look on the other side, on basic, we have more hydroxide ions. At 7, there's an equal amount of hydrogen and hydroxide ions, so it's called neutral. Another way to view the changing amounts of the hydrogen ions and the hydroxide ions is just in this chart right here. But I want to talk about it in a logarithmic way. Logarithms are something that you're going to do in Math 20 and 30. It's something that we call exponential. And the best way to remember it is like on an earthquake scale. Because when we learned about earthquakes, if you have an earthquake and on the Richter scale, it's like at a Richter scale of like a 7.4, what that means is it's actually 10 times stronger than, what would be at 6. So every single time you move up a number in the pH scale, it gets 10 times worse. So if you have a pH of 7 and you move down to a pH of 6, so it's getting more acidic, that substance is 10 times worse than it was at 7. If we have a pH of 5, it's 10 times 10, so it's 100 times worse. If we have a pH of 4, it's 10 times 10 times 10, so it's 1,000 times worse. So you understand that as we go backwards and as we get closer to like a pH of 0, which is literally sulfuric acid, we're looking at a pH of like 10 to the minus 14. So that's a lot of, or sorry, 10 to the 14 zeros. That's like a million bazillion times worse. So pH is on a logarithmic scale. It gets 10 times worse every time it gets more basic or every time it gets more acidic. And so every number on the scale moves up by 10. Does that make sense? So when this scale is just looking at the hydroxide and the hydrogen ions, and it shows you that the hydrogen ions are the most at a pH of 0, and the hydrogen ions are barely any at a pH of 14. When you look at the hydroxides, you can see that at the end there, that there's a boatload of hydroxides at 14 and 0 at 1. And so we're just looking at a pH at an exponential level. It's 10 times 10 times 10 times 10 worse, which is why if I stuck my hand in the sulfuric acid, then it would start to eat away my skin very quickly, and I would be in a lot of trouble. So a substance with a pH of 4 is more acidic than a substance of pH of 5. And remember, it's 10 times more, and a substance of pH of 11 is stronger than, as a stronger base than a substance with a pH of 8.5. So there we have it. You can take a look at that scale. So measuring the strengths of acids and bases is the next thing that we're going to talk about, and I'm going to show you a little bit of how we're going to do that today in the lab. Acid-base indicators are liquid chemicals or liquid pieces of paper which will change color when they get in contact with different types of acids or bases. Some acid indicators are phenolphthalein, which we don't have in the lab, methyl red, bromophenol blue, phenol red, methyl orange, red wine, cabbage juice, and beet juice. Okay, and so we have all of these things that we're able to look at, and we're able to kind of take a look and see which types of this stuff are indicators. Liquid acid-based indicators will give you an approximate pH value. Litmus paper also gives you an approximate value, which we're going to look at in a second. And so we already talked about how blue means base and red means acid. So anytime these pieces of paper turn blue, it means it's in a base. Anytime this piece of paper turns pink, it means it's in an acid. Okay, some litmus paper also, like I have right here, changes a whole bunch of different colors. And so we'll take a look at it in a second and we'll test it out. The first base that we're going to test is the Drano. So we already know that this Drano is basic. We know that it has a pH of probably greater than 7. When we test it with litmus paper, this pink litmus paper is going to turn blue because it's a base. So you can see here that when it touches the Drano, it's indicating that it is a base. So pink litmus paper is going to turn blue in the presence of a base. If we want to take a look at what this acidic piece of paper, oh sorry, we just did that. If we want to take a look at this, basic piece of paper and we dunk it into a base, it's going to stay blue. So you notice that the color doesn't change. B means blue for base when it comes to litmus. There's other universal indicators that we can use here too, which is this yellow sheet here. There's a little bit of just like a table that tells you which color each pH number is indicated by. So when I dump my universal indicator into my beautiful Drano, it turned purple. If I look on the scale here, I can see that purples go from 11, 12, 13, and 14. And according to my adjustments, it looks like it's about a pH of 12, which means it's quite basic. And so that's a universal indicator, an example of how that can work with a different sheet of paper. If we were to take some of our sulfuric acid and pour it into a glass, we need to be extremely careful. Obviously, we know that this is extremely acidic. So again, if we were just to take a look at using a piece of blue litmus paper, when I dump it into the sulfuric acid, it changes into a pink color because we know it's extremely acidic. It doesn't tell us the number, but it at least notifies us that it's acidic. If we use another one of the universal indicator pieces of paper, we should be able to get a better idea of which pH number it is, and by just looking at our pieces here. So if we go ahead and we dump this in to our sulfuric acid, here we go. It turns kind of a pinky purple color. So going on to my, oh, never mind. Yeah, so going on to my pH scale, I actually notice, if you can see, that the pH of 0 or 1 is somewhere in there. So this is extremely acidic, all right? And so that's how we use litmus paper and universal indicators of litmus to identify the pH of substances. So moving away from the litmus paper, we can use a universal indicator like red cabbage. You blend it up in a blender, you put some water in, and you make a universal indicator. It smells so bad, it smells up your whole house for like at least a day. So I don't recommend it unless you want everybody to leave. It's disgusting, and I don't like eating cabbage anyways. But this indicator will actually indicate whether something's an acid and a base, or a base, and it will actually tell you what the pH is by turning the color that it wants to. I haven't strained out all of the cabbage juicy thingies, so hopefully it'll work. So let's check it out. So now here we have a little bit of universal indicator, all right? And we're going to pour some of our acid into, or our indicator into our acid. I believe that this was the sulfuric acid, and we'll find out, because if you look on a scale of how cabbage juice turns, cabbage juice usually turns things that are acidic, pink, or kind of a red color, and if it's basic, it will go green or some sort of a dark blue color. So let's take a look at this one. So you can see what automatically happened is it turned the liquid red, which, when I throw the scale up on the video, you'll notice, and you can actually match the color to what the color it is on the pH indicator. This cabbage juice is a universal indicator telling me what the pH of this is. So let's check out our base. This is Drano. So Drano we know is basic. So what color is it going to turn? It's going to turn a different color when we add the same beautiful cabbage juice into it. So here we go. If we pour this in, we notice that it turned green, and then all of a sudden it turned kind of this red color. And so we can take a look at that on the indicator as well. All right, so now that we've looked at different different acids and bases, and we've looked at ways that we can put them on the pH scale, we need to really understand what neutralization is. Neutralization is literally when you put an acid and a base together. So that would be like me putting Drano, which would turn this kind of yellow-green color, and this acid together and mixing them to neutralize them. When we get a perfect neutralization, we actually make water and salt. So actually, by me neutralizing these two substances, I'm able to dump them down the drain, because the pH no longer is extreme, like this is an acid, a pH of like 1 or 2, and this is an extreme base, maybe a pH of like 13. If I mix them together, what I get is water and salt, two really harmless substances, and that's why we call it neutralization. Neutralization has a pH of 7. And so in order to do a neutralization, you do take an acid and a base. You need to measure certain types of concentrations and certain amounts, but ideally what you do is you'll be able to bring it to a more neutralized state. So now that I've added my acid to my base, I should have some sort of a neutralization. And I don't want to touch that because I really don't know what's going on in there. I just know it's neutralizing. The air and the bubbles in there, I was a little bit scared it was going to go overboard, but it should neutralize the acid and the base there. And it should be good enough for me to touch. So a way to clean up a spill or an acid spill when you have one is to actually take a base and to put it on top of the acid to neutralize it. It's a way that we can actually clean up our messes when we run into problems and we have something that's too basic or too acidic. We just add the opposite thing. So if a large base spills on the ground and we add a little bit of acid, we're able to neutralize the solution and it isn't as strong anymore. Something important to understand. So acids and bases of equivalent strengths, when added together, will form a salt and water. So just remember that we can't just put an acid of like a super strong base, like a 0 or a 1, and try to neutralize it with a base that has a pH of 8. A pH of 8 is only one step ahead of neutralization. It would take an awful lot of that base to neutralize it. So just understand that if you're ever asked a question about how to neutralize a substance, you want to have equal amounts or equal concentration when you do the neutralization. So here we have hydrochloric acid with sodium hydroxide, and we're able to produce salt and water. And that's pretty awesome. And the pH will be approximately 7, which makes it safe to handle and dispose of. A strong acid can neutralize a strong base, and a weak acid can neutralize a weak base, but if we add 100 milliliters of a strong acid to 50 milliliters of a strong base, the result will be a weaker acid because we didn't add the same concentration or the same amount. So just make sure that you're being equal with your strengths of bases as well as your concentration in order to do the equalization and the neutralization reaction correctly. So antacids are things that we take when we eat too many wings or we eat too much vinegar and we put it in our stomach. And so usually you create a whole bunch of excess stomach acid to digest a lot of food. And so antacids, which is a weak base, will actually react with the strong acid in the stomach to produce a weaker acid, and therefore it doesn't hurt your body because your body is used to having an acid, so it's not hurting you even though there's some acid in there. The last piece of this unit and this part is acids and pollution. We need to understand that industrial processes or big, huge buildings that produce a lot of smoke make a lot of acid and put it into the environment. So when we burn fossil fuels, when it produces a lot of carbon dioxide, a lot of sulfur dioxide, and a lot of nitrogen oxide. And these compounds dissolve in water droplets that are in the air and they form acid rain. So if you remember back in grade 7, we took a look at acid rain and what it can do to statues, and it literally just eats up the stuff in our environment, like bridges, anything that's stonework, it just totally dissolves it. So acids are corrosive, they dissolve metals, they dissolve even stone, and so it actually can really hurt the infrastructure that we use to build. But not only that, when we get acid rain, it actually can cause lakes and rivers to become completely acidic, which is completely harmful to our plants and our animals. We can't have acidic lakes. All right, it destroys forests, it destroys wildlife. In fact, in Edmonton, where we see acid rain the most is actually on the side of the city where it's close to Sherwood Park, because that's where all the industry is, or the oil industry. And at that location, we're putting a lot of smoke into the air, and there are times where we see a little bit of acid rain. If we get too much acid rain, it can destroy a lot of things. Acids produced from pollution. So carbon dioxide dissolves in water, dissolves limestone, but is a weaker acid than most. Used to make fizzy beverages. You can dissolve a penny in Coke. So Coke literally is quite acidic. So acid rain really damages our plants and our animals. In fact, fish can't live at a very high pH. They'll just begin to die. And so we need to make sure that we limit the amount of gases that we put into the atmosphere so that we limit the amount of acid rain that falls on our own infrastructure, but also in our ponds and our lakes and our rivers so that we don't kill all the animals there. If we neutralize acid rain, there are thousands of dead lakes in Ontario and Quebec from pollution caused by manufacturing. We don't have as many here, but Lake Wabamun used to be an example of something that was on the verge of becoming a dead lake. So a dead lake meaning there's no animals that live there. Lime, so calcium hydroxide dissolved in water, is sprayed over lakes to actually neutralize them to get the life back. So we can actually go in and humanly neutralize a lake and bring it back to life so that the acid isn't killing the animals in there. Some neutralization reactions are just there for you. Just to understand, humans can just so easily break or shut down a lake by putting too much acid in, but we can also go back and neutralize it by adding an acid that's not harmful.